experiment 23. That's the last lab. And the previous labs, that would be this week's 22 and 23. Those will be due Monday by midnight. So it's good news, no more labs. Yeah. And there's a survey that SWIC sent out. It's called the COVID-19 SWIC Institutional Response Student Survey. It's a questionnaire about students' opinions on how well SWIC handled the shutdown. And they say that it takes about 5 minutes to complete. I haven't actually seen it, but that's what I was told. And this survey is available through Monday the 11th. And your input will be greatly appreciated. They're anxious to find out, what students' opinions were about how the shutdown was handled. So if you could fill that out, that'd be very useful for the people running SWIC.
Hey, Mr. Clerk, could you repeat what you just said? I just got on, so just that part about what the survey is and stuff.
Oh, okay. It's a survey, and it's asking for students' opinions on how well SWIC handled the shutdown. And so they're seeking student input on that, and they said the survey takes about 5 minutes to complete, and it'll be online through May 11th. So if you could respond to that, it would be greatly appreciated.
Okay, gotcha.
Okay. And then I also mentioned the labs. We are all finished with labs as of today. Well, actually, one more report is due, which would be experiment 23. I did receive one finished experiment 23 report today. That's good news. So just need the rest of you to send that in, and we're all set with labs. All done.
Okay.
Okay, now the next exam is Monday, May 4th, and that'll be the usual where it's posted on Blackboard at 8 a.m. and due by midnight. And it'll cover the last part of chapter 17, electrochemistry, that we didn't cover in the last exam. And specifically, that would be pH, KSP, and also battery capacity. And that it's very similar to the part 3, chapter 17 lecture, and all of that in the PowerPoint MP4 video. If you'd like to see examples of that, or we could go over that tonight too if you want. And then it'll also cover chapter 19, which we're currently on, coordination chemistry, and chapter 21, nuclear chemistry. And then next Wednesday, May 6th, is the lab exam. That will be posted on Blackboard at 8 a.m. due by midnight, and it will cover the lab calculations. And probably this weekend, I'll send out a bunch of graded labs. It took a while to get all those scanned in, but I'll be sending those out, and you can have a look at the calculations and go over those to get ready for this lab exam. Okay, coordination chemistry. Let's move on in chapter 19. Okay, chapter 19 is about crystal field theory. And there are two sets of notes posted on Blackboard. One is the usual one I put together, which has examples. There's an answer key in it. We went over that last class, Monday. And then there's also a part about 10 pages long from Koch and Treichel textbook. So it has KT at the end for the name of the authors of that book. And it's a very good description of crystal field theory. So tonight we'll be going over a lot of examples with this. We went over most of these KT notes and the other notes last time, but tonight we'll do a lot of examples. Okay, so let's look at the effect that an octahedral crystal field would have on a metal ion's valence orbitals. Okay, here's the usual description we have for the valence orbitals in a metal ion. Like for instance, a transition metal, they have their D shell of orbitals. And they also have an S shell. And normally those S electrons are lost whenever they undergo a reaction or they ionize. So the S electrons come off first, and the ion actually has a remaining shell, which is based on D orbitals. And in a free metal ion, that is, when we say free, we mean in a gas state, there's nothing around to interact with it. There's nothing to distort the orbitals, and in that case, all 5 orbitals have the same energy. And it's a spherically symmetric field, so in any direction you go, it's basically sees the same thing, which is essentially nothing. And that's very different from the field it has when it's in a chemical compound or in a solid. Okay, so here's an example of an octahedrally bound metal ion. Instead of 5 orbitals all having the same energy, we have a set of 3 orbitals and a set of 2 orbitals. So in both cases altogether, we have 5, but whenever we start imposing an octahedral field on the free metal, it raises the energy and splits these, and they're labeled with symmetry tags T2G and EG. And you don't need to know like the derivation of those names, but I'll just mention it as an FYI. Each of these letters actually means the symmetry of these orbitals. Like an octahedron, if you'd look at a little model of an octahedron, you'll see it's composed of a bunch of triangles. They're all equilateral, and it's related to a cube. If you take a cube and look at it along the diagonal axis, you'll see that it has cubic, or it has triangular symmetry also. And the T and the E correspond to different symmetry operations like rotations and mirror planes and inversions and that. And the G stands for Girard. We have Girard and non-Girard, which corresponds to the whether or not these have an inversion. But that was just an FYI. So, these labels really have a specific meaning. They're not just like pulled out of a hat. So anyway, in an octahedral field that is created when, let's say, 6 ligands come up and they want to react with this metal. So they come up and they spread out and they kind of latch onto it. And because of their mutual repulsion, they're spread out as far as possible, and they naturally form the vertices of an octahedron. And that causes the orbitals to split because of their symmetry into a T2G group, which is 3 orbitals, and an EG group, which is 2 orbitals. And they're split in energy. The T2G has a lower energy than EG, and this on the screen, energy increases as we go up. So the lower energy level is T2G and the upper level is EG. So that's how the energy levels are configured in an octahedral field. And the delta symbol is known as a crystal field splitting. The splitting refers to the splitting of these 5 free metal ion orbitals into the 2 groups, the T group and the E group. The distance in energy, like measured in joules, typically would be called delta, the crystal field splitting. Now we can do this in not only an octahedral field, but tetrahedral. If we did the same sort of experiment with a tetrahedral molecule, we'd see it splits similarly, but the energy levels are reversed. In fact, in this case, the group of 2 has the lower energy, and the group of 3 has the higher energy. So it's the opposite of an octahedral field setup. In this case, E is lower, T is higher. This is for a tetrahedrally bound metal ion. So that'd be a metal ion with 4 ligands attached, and each ligand is spread out as far from one another as possible, and that naturally forms a tetrahedron. Okay, the next kind of geometry we encounter in coordination chemistry is square-planar. It's like an octahedron with the top missing and the bottom missing. So we're left with a square, nothing above and nothing below. So in this case, we are split into 4 levels. Actually, there's a mistake in that. In this, that should say square-planar. So see, fix that. So it's a square-planar bound metal ion. So the 5d orbitals in the free metal ion, when subjected to a square-planar field, they split into 4 groups. And they each have their own specific delta value. Now, how do we fill these orbitals with electrons? The rules are the same as what you're likely familiar with already. We use the Aufbau principle, which is fill them in order of increasing energy, low energy first. Pauli exclusion principle, which is 2 electrons cannot occupy the same orbital unless they have opposite spins. And Hund's rule is the empty bus seat rule, which is that the electrons grab their seat, or like their orbital seat on the bus, one at a time. They each have their own seat, and only after all the seats are occupied do they start pairing up. So if we were filling a D shell, we would start out with an electron spin up in the first orbital and go all the way across, fill them all so they're singly occupied. And if we have extras, and those go in to pair up, spin down. So this would be an example of a filled D shell for a D6 electron configuration. So let's look at how that works out if the metal is bound in an octahedral complex. We have our T2G at the bottom and EG at the top, and we have our crystal field splitting. And if delta is small, the electrons have no problem with populating both levels like this. Like the first 3 would go in the bottom, and because delta is small, it's really no problem for them to occupy the E level. So the next 2 can go up there. And then the 6th one would go back and start over at the bottom. So if delta is small, that is if the crystal field splitting is small, the electrons fill in this manner. This particular configuration is called the high spin configuration. And we get the maximum number of unpaired electrons this way. It's called high spin because it's so easy for the electrons to populate the upper orbital with parallel spins. So we get the minimum number of spin pairs. And whenever we have lots of unpaired electrons like this, that gives rise to magnetic behavior. This particular example is known as paramagnetic. It's a small magnetic field around the molecule, and it's caused by these electrons which have parallel spins. In a solid, for instance, well, not a solid, let's say we melted iron. Like iron is a D6 element, and it has lots of unpaired electrons like this. And if we heat it up and melt it, so it's easy for those electrons to orient in a parallel way, and then, like, for instance, take molten iron and expose it to a magnet and get them all lined up, and then quench that by dumping it into cold water to freeze it and lock it in place, and we can make a permanent magnet. But normally these, one molecule might look like this, and the next molecule might have the opposite spin. So collectively in a liquid or random solid, they'd cancel out. But in a permanent magnet, they're all lined up. Neighbors all have the same orientation. So we get permanent magnet that way. Okay, let's look at the other case. What if delta is large? So if delta is large, we get an order of filling like this. The first three go in the bottom, and because delta is large, they can't just jump up to the top level. They have to pair up in the bottom level. So we end up with everything spin paired. This is known as the low spin configuration, and we get the minimum number of unpaired electrons this way. And this particular case is known as diamagnetic, and that means everything is spin paired. Like there are no unpaired electrons here. Okay, so that was the low spin value of delta, which is large. The larger delta is, the farther these levels are apart, and the least number of unpaired electrons we get. So, and when there's absolutely no unpaired electrons, we call it diamagnetic. Okay, let's look at the periodic table and counting valence electrons in transition metals. Let's pick chromium. Chromium's a D4 first row element. Its neutral state is S2D4. So that the zero here, chromium 0 means ground state, or it's neutral. So it has two s electrons here in positions like 19 and 20, and then 21 through 24 are the 4d electrons. So it's S2D4. So if we have a chromium 2+ ion, it'll lose those two s electrons first, and leaving the 4d electrons. So the chromium 2 ion is a D4 configuration. And this configuration is used to figure out the geometry of a complex. Another example is copper. Copper is S1D10. It's one of the excluded. It follows the Lewis guidelines for, or yeah, the guidelines for assigning electron configurations, not Lewis, but anyway, it's in the D9 column, which is a special column because these are all of our stable metals: copper, silver, gold. And if they get one more electron, they can be stable, so they borrow an s electron and live as S1D10. So if we ionize copper, take away an electron, it loses that s electron. And it should be a D10. Copper plus. Yeah, it should be D10. That's a typo. Okay, so fix that. There, it's D10. Okay, so let's look at a couple of questions. How many 3D electrons does manganese 3 plus have? And for reference, here's a periodic table. So manganese is right here. So if we have an Mn3 plus ion, how many d electrons does it have? How about Elizabeth? Are you out there?
Mic on.
I'm not really quite sure, but I kind of want to say 5, but also I don't really know what I'm doing.
Okay. Well, that's close. Let's see, manganese is 1, 2, 3, 4. It's D5, S2. So 5 and 2 make 7. Yeah, and if it's 3 plus, we would take 3 away from the 7 and get 4. So let's see what the answer is. Yeah, the answer is 4. So you were close. Okay, how about silver plus? How many 4d electrons does silver plus have? Does anyone want to take a stab at that? Here's silver, it's in the same column as copper. Well, Brennan. Let's see. 4d electrons is silver. It'd be 10. It's the same situation as copper. It's in the same column. So copper, silver, and gold all behave the same way. Their neutral is S1D10, and their +1 state is D10. They ditch the S1 electron. It goes away, so they're left with D10. Okay, how about this one? A +3 first row metal has 7 3d electrons. Which metal is it? So we're given that it has the ion in a +3 state has 7 electrons. Which one is it? So and it said the ion's +3, right? Well, we can look at this on the video, I guess, for practice, but it would be nickel. It's easier to do on a periodic tables right in front here on this same slide. Okay, so let's look at some applications of this crystal field
Mic
theory.
off.
Let's predict the electronic configuration of iron 2 in an octahedral complex. So here's iron. The first step is to figure out its electron configuration. So iron happens to be a D6 metal, so this is need to fix that. That should be iron 0, the neutral. Yeah, iron 0 is S2D6. So that would be 8 electrons altogether. So if we count the number of boxes from the left, we get 1, 2, 3, 4, 5, 6, 7, 8. And then if we ionize it twice, we get iron 2 plus. It loses the 2 S's and we have D6 remaining. So here are the energy levels that we populate with those 6 electrons. So if in the case of a small delta, that is a high spin configuration, the 6 electrons go in like this. First 3 go in the lower level, and the next 2 go in the upper level, and then we start pairing off with the 6th. So we end up with this situation with 4 unpaired electrons. And this situation would be paramagnetic because we have the unpaired electrons. And an example of that would be ferrocyanide, which is iron attached to 6 cyanides. Now, the other alternative would be the large delta, low spin. So let's populate the orbitals. In that case, the first 3 go on the bottom, and then it's large delta, so they can't actually make it up to the other level, so they populate the bottom one. Again, everything's spin paired, and we get a diamagnetic molecule. And an example of that is iron attached to 6 waters. Okay, so now let's look at cobalt attached to 6 ammonias, low spin, and predict the magnetic properties. Here's a row of the periodic table. Cobalt is D7. And when it forms an ion, it loses a D and 3 S. It loses 1 D and 2 S electrons, leaving D6. And D6 happens to be in the group that's listed in the class notes. There's a table in there, I think on page 2, that shows how to relate the electron configuration to coordination number. And this particular coordination number is likely to be 6, which would be an octahedral molecule. Given that it's octahedral, the levels are split like this, with 3 at the bottom, 2 at the top, with the value of delta being small. That was given up here in the question. Delta is small. Oh, sorry, no, delta is large. It's low spin, so that means large delta. So these are far apart. Let's populate them. All 6 go in the lower level. It's diamagnetic. Another example, let's look at manganese attached to 6 cyanides. This is low spin also, meaning large delta. Here's manganese. Manganese is D5 as a neutral. As a +2 ion, it's S0D5, and we figured out it's +2 by looking at this formula. We have a cyanide attached 6 times. Each one of those carries a -1 charge, so altogether we have 6 minus charges from the cyanides, and we have 4 potassiums attached to it. So we know that without those 4 potassiums, it'd have a +4 charge overall, or I mean a -4 charge. So the 4 potassiums even it out, and we're left with Mn2+. Now the coordination number here for this type of ion is 6 from that table in the class notes. So we assume it's octahedral, then we draw our orbitals like we did before. And we're given that it's a large value of delta, low spin. So we populate this in with our 5 valence electrons. And this time they don't completely fill, and we're left with a paramagnetic situation. So this one is an example of a low spin that happens to be paramagnetic. Okay, let's look at a high spin example. Here's an iron with 6 fluorines attached to its counterions, 3 ammoniums. So iron, again, is D6, S2 is a neutral. And we need to figure out the oxidation state of iron in this complex. We know that from doing the accounting for the 6 minuses for the fluorines and the 3 positives for the ammoniums, that it must be a D5. If it's D5, it's in the category of octahedral complexes. So we have the same set of orbitals, 3 on the bottom, 2 on top. And this time it's high spin, so delta is small. So the electrons can easily populate both levels at the same time. So the first 3 go on the bottom, the 4th and the 5th go on top. So this has everything unpaired. All 5 are spinning the same direction, yielding a paramagnetic molecule. By the way, if any questions pop up, feel free to interrupt. Okay, the next one is zinc attached to 4 chlorines with 2 ammoniums as counterions. So here we have 4 ligands. And zinc is over at the end of the D block. It's a D10, S2D10 metal. In this compound, zinc is 2+, so we get rid of the 2 electrons, and that gives us 10 D electrons. This time the coordination number is 4. And according to the table in the class notes, whenever we have a filled D shell, it's very likely that we have a tetrahedral molecule. And it so happens that all tetrahedrals are observed to be high spin. So anytime we hear that a tetrahedral molecule is involved, we automatically know that it's a high spin situation. So tetrahedral molecules had the order of levels reversed. They had the 2-member set at the bottom and the 3-member set at the top. It's high spin, so delta is small. So let's fill these with the 10 electrons. First 2 go in, spin up, then they pair up. Actually, they should be going, I'll fix this, but they should have, the 3rd one should go on top, not down at the bottom. But anyway, they all end up pairing up like this. So we get all 10 spin paired, and this is a diamagnetic molecule. We probably could have figured that given that we have a D10. So we automatically know that all 10 little orbitals in this set would have to be filled and paired. So it would have to have yielded a diamagnetic molecule. Okay, we can also use this model to compare the magnetic properties depending on geometry, like whether it's tetrahedral or square-planar. So let's look at the magnetic properties of this nickel complex and tetrahedral and square-planar geometries. So nickel has an S2D8 configuration as a neutral. As a +2 ion, it's S0D8. And from the up here from within the brackets, we can tell it's coordinated to 4 chlorines. So the coordination number is 4. And we also know it's a D8 shell from the configuration. And So based on the table in the notes, this must be a square-planar molecule. It's not necessarily, but it's very likely to be square-planar. We could confirm that by measuring its magnetic properties. So let's look at the tetrahedral case. Tetrahedrals are always high spin. Here are the levels for tetrahedral. It's high spin, so delta is small. And let's populate those with 8 valence electrons. So there's 1, 2. Those should be going on top first. I guess I'll fix this one as well. But we'd end up with the same situation. It would be paramagnetic. So after we put our 8 electrons in, we get these 2 unpaired. So this would be paramagnetic. Now let's compare to square-planar. Square-planar's levels were split very differently from the others. We get 4 separate sets. So the first 2 go in the bottom like that. And then the next 2 go there, and the next 2 go in the third level. And we're out of electrons. So this would be spin paired regardless of what small delta or large delta, and diamagnetic. So anyway, this is a way we could tell these 2 molecules apart, like, or verify what type of geometry it has by measuring its magnetic properties. If experimentally we would find out that it's diamagnetic, then that would point to the square-planar geometry. On the other hand, if it were paramagnetic, then that would point to the tetrahedral geometry. Okay, so we've talked a lot about the splitting parameter, delta. What determines the size of delta? Well, delta depends on 3 things. First, it depends on the strength of the ligand. Second, the charge of the metal. And third, the size of the metal. And delta is proportional to each one. So as the strength of the ligand increases, so does delta. As the charge of the metal goes up, so does delta. As the size of the metal goes up, so does delta. So here are a few slides from Jesperson to discuss the same thing. Okay, here he says, first, delta depends on the nature of the ligand. Some ligands produce larger splittings than others. And as the ligand field strength increases, so does delta. And by ligand field strength, they simply mean the ability to cause the splitting of d orbitals. And one example is cyanide always gives large splitting, whereas fluoride gives small. And as a result, the ligand basically determines the value of delta, get a unique delta for each ligand. And this ends up causing different colors to occur depending on which ligand is attached. This gives rise to the spectrochemical series. Ligands that produce a large delta with one metal generally produce the same large delta with other metals. And they can be arranged in order of their ability to cause a large delta. And that's called a spectrochemical series. And here it is in order of decreasing strength. On the left, we have cyanide, which is the strongest. And on the right, we have iodide, which is the weakest. And then we have water and ammonia and oxalate, which are around the middle. So as we travel along from the right end, that is iodide, and we move towards the left end with cyanide, the value of delta increases. So on the right side, we'd have small delta, that would be high spin. That would most likely be paramagnetic. And on the left-hand end, we'd have large delta, which is low spin and more likely to be diamagnetic. So with the same metal, then cyanide produces the largest delta, iodide produces the smallest delta. Now, the second thing delta depends on is the oxidation state of the metal. So delta increases as the oxidation state increases. So for example, neutral iron would be below iron 2, which would be below iron 3. So iron 3 would have the largest splitting. Iron 2 would have a smaller splitting. And there's a reason for this, and that is as electrons are removed from the metal, the charge on it becomes more positive and it becomes smaller generally, which means that the ligands are attracted to the metal with more strength. And it causes greater repulsion in certain types of orbitals. This dx squared minus y squared, dz squared are the two orbitals in the EG group. So this leads to greater splitting of the d orbitals and a larger value of delta. The third thing delta dependent on is the row on which the metal occurs, which is related to the size. So delta increases as we go down a group. So one column of the periodic table is iron, ruthenium, and osmium. So for the same oxidation state of these metals, we would get osmium having the largest splitting. It's the largest metal. And then ruthenium would be smaller, followed by iron. So we can compare metals in the same column. And other examples, nickel and platinum. Those are both D8. And of these, platinum's below nickel, so it would be larger. It has a larger value of delta. And qualitatively, the reason for this trend is that for the larger element, we have more diffuse d orbitals that extend farther from the nucleus towards the ligands, and that causes more repulsion between them, and we end up with a larger value of delta. Okay, so let's look at these examples and try to figure out which of these complexes has the larger delta. So if we have iron 2, this should be 2 plus right here. So anyway, the plus is for some reason down here by the or, but it should be moved up to the 2. So we're comparing iron 2 plus to iron 3 plus, which has a larger value of delta.
Mic on.
How about Diana?
I'm not really sure.
Well, Brennan. Yeah, yes. So iron 3, the higher the oxidation number, the larger the value of delta. Okay, then, yeah, the next one, we're comparing chromium 2 plus to molybdenum 2 plus. So these elements are in the same column the periodic table. So really here we're comparing size. Chromium's small, molybdenum's large. Okay, Jacob, how about you?
Would it be the MO?
Right. Yep. Yeah, the answer is molybdenum. And the reason is that it's larger, so it has a larger value of delta. Okay, the next one's platinum. Looks like if overall this complex has a -2 charge, so platinum must be +2. And it's attached to cyanide and on the left, and then on the right, it's attached to chlorine. So which of these would have the larger value of delta? Right, yeah, the cyanide. Yeah, there's a spectrochemical series. Yeah, cyanide is on the left. It has the
Mic off.
strongest ligand strength of all. So definitely the platinum cyanide complex would be a larger value of delta. Okay, let's look at these four complexes. Which of these has the largest delta value? Here, for reference, here's the spectrochemical series. So by the way, it includes EN, which is a ethylene diamine. Okay, Elizabeth, how about this one?
Is it A?
You're right. Yes, it's A. Yeah, EN is the it's the one farthest to the left. Yes, so you're right. Okay, let's look at another example. Whenever cobalt-3 sulfate is dissolved in water, the complex it forms is diamagnetic. But if sodium fluoride is added, it becomes paramagnetic. Why would that be? So let's look at where cobalt lives. It is D7. And we know it's a +3 ion because two of them are attached to 3 sulfates. So cobalt has to be +3, which makes it a D6. And we know from the table in the class notes, it's not D8 and it's not D10, which means it very likely coordinates to 6 ligands, making it octahedral. So whenever this cobalt sulfate is put in water, here's the reaction. We get 6 waters attaching to it. So we end up with the trivalent complex ion. I get the name of it would be the hexa-aquo cobalt-3 ion. Now, whenever we add sodium fluoride to it, what would happen? So it reacts with it. We know that because it changed the magnetic properties. So if the cobalt water-based compound is mixed with fluoride, the fluoride could displace the waters. So we end up with the hexa fluoro cobalt-3 ion. So we really are looking at the magnetic properties of two different compounds. When initially dissolved, we had the water-based cobalt compound, and after the fluoride was added, we have a new compound, which is a fluorine-based cobalt. So to find out how these compare, we need the spectrochemical series. We have water compared to fluorine. So here's the first compound, this is the one formed on initial dissolution. It's attached to water. Here's where water lives in the spectrochemical series. The second compound, it's the fluoride, and there's where fluorine lives in that series. So let's make a configuration for each. It's octahedral, so we have the T group at the bottom, E on top. And let's fill in the electrons. So we have, there's the first three. And there's the next three. And it's diamagnetic. Everything is spin paired. So we were told in the question that this was diamagnetic. So that's why we could assume it's a large delta, low spin. Now, let's look at the other compound. This one's small delta, high spin, because it's observed to be paramagnetic. So anyway, let's fill the electrons in. So they fill in this way with 5 parallel, and when we add the 6, it pairs off. So we end up with 4 unpaired electrons, which makes it paramagnetic. So this would be an explanation as to why the cobalt complex changes from diamagnetic to paramagnetic when sodium fluoride is added. Okay, so we can also use the crystal field theory to explain relative stabilities of different oxidation states. For example, chromium +2 is easily oxidized to the +3 state in these two complexes. And to explain that, we can look at the electron configurations. The chromium's electronic configuration is S1D5. And if we have chromium +2, we remove 2 electrons and we get D4. And compared to the chromium +3, we would have removed 3 electrons and ended up with D3. So we can use those 3 and 4 electrons in the D levels like we have been doing and compare. So here is chromium +2, which has 4 valence electrons. They draw the levels a little differently. They just use horizontal lines instead of boxes, but the meaning's the same. So the 4 electrons go in with parallel spins with a small delta situation. So this would be an example of the chromium 2+, which is easy to oxidize. So we're trying to explain why it is easy to oxidize. So if we compare that to chromium +3, its configuration looks like this. It's the same as what's above, minus that high energy electron. So if we oxidize chromium +2, that means, in effect, to take away that high energy electron, leaving the 3 lower energy electrons, which makes it favorable in terms of energy. So this would be a way to explain the observation using crystal field theory of why it's easy to oxidize chromium 2 to chromium 3. Now, how about color? The most interesting part of this, I think, is why things are colored. So when light is absorbed by a molecule, we're basically moving electrons from a lower level to a higher level. And if there's a large energy difference between the levels, then you'd need more energy of light. And so instead of visible light, you might need UV light or even higher. For example, NaCl appears white, and because no visible light is absorbed. If the energy difference is small, then visible light could be used to promote electrons from one level to the other. And an example of that is typical transition metal complexes. Okay, here's for reference the spectrum. Roy G. Biv, we have red on the left. It has the lowest energy, longest wavelength, 700 nanometers. And on the right, we have violet with a wavelength of 400 nanometers. The energy of the light is equal to h nu. H is Planck's constant. Nu is the frequency in cycles per second. And then we have the whole thing could be expressed alternately as hc on lambda, where c is the speed of light and lambda is the wavelength of the light. So as the frequency goes up and the wavelength goes down, the energy goes up. So when we go from left to right, the energy goes up, wavelength goes down, and vice versa. When we go from violet to red, the energy goes down, but the wavelength goes up. So the lowest energy is red, highest energy is violet. So let's look at the absorption of light. Here we have a ground state on the left. We have 3 electrons in the T group in an octahedral complex. We hit it with light, and that promotes one of the electrons from the lower level to the upper level. And consequently, it absorbs certain wavelengths of light correspond to the energy difference, of which the size is measured by delta. So the larger delta is, the more energy is required, and the shorter the wavelength. So the light energy that comes in and is absorbed by the sample is equal in energy to the value of delta. And that promotes the electron from the lower level, which is the T2G, to the upper level, which is the EG. Now that is how we would explain the absorption of light. But if a molecule absorbs a certain color, certain energy of light, and transmits all the remaining part of the visible spectrum, okay, what color do we see? We use a color wheel for that. For example, if we look at the color wheel, here's red. If we go straight across, the complementary color to it is green-blue. So a molecule which absorbs red light would transmit green-blue light. So we'd see a solution that's green-blue in color. Another examples, violet blue. Violet blue is here. If we go straight through the center, we arrive at yellow. So if a compound absorbs violet blue light, we would see it as yellow. Okay, now let's look at another example of absorption of light. Here's a D6 configuration in an octahedral field. And let's look at the case where delta is small. If delta is small, then low energy light, such as one with a large wavelength like red light, could promote an electron from the lower level to the upper level. So we're going to hit it with red light And then that would promote one electron from one level to the other. Okay, question. What color is the solution containing this ion? And there's a color wheel for reference. Okay, Diana, what color do you think the solution would be?
Red?
Well, it absorbs red light. So what color is transmitted?
Would it be like, go ahead.
Yeah, right, we go through the center, the color wheel, and get green. Yeah, so we'd see it as a green colored solution. So I actually just looking at the color of a solution tells us size of delta. So if we saw it as green, that means it must be absorbing red, and red has a long wavelength, low energy, so we know delta must be small. How about another example? How about large delta? In this case, violet light promotes an electron like this. It's the same situation as before, only delta is larger. So the levels are farther apart. It requires more energy to promote the electron. So what color would this solution be? Jacob, are you out there?
Yeah. If the delta is large, violet.
Well, it absorbs violet.
Right, it absorbs such as violet light.
Right, so what color would the solution be?
Would it be the same as the last one?
Yellow?
Be the opposite?
Yeah.
Yellow.
Right.
Yellow?
Yeah, it's yellow. Yeah, straight across from violet. Here's violet, and go across yellow. Yeah, so the answer is yellow. The yellow solution contains something that's absorbing violet light. There's another slide from Jesperson. I think we've already seen it. Oh, it's explaining a little more. Oh, yeah, it's a little more, and like another example, this one with chromium, it's the same principle, only in this case, it's absorbing yellow light. Yellow light corresponds to around 600 nanometers wavelength, or 5 times 10 to the 14th hertz. So if it absorbs yellow, it must transmit violet. So the solution would appear violet. Okay, let's look more at the effects of the ligand on the splitting parameter. So we already know the color absorbed depends on the size of delta. As delta increases, the light energy has to increase. And so the frequency of the light has to go up, the wavelength goes down. And so for transition metals with the same oxidation state, delta depends on the ligand.